Hello everyone. Today our topic is parallel priority interrupt. In the previous video, we discussed two methods for implementing the priority interrupt: the polling software method and the daisy chain hardware method. The daisy chain method consists of a serial connection of all the devices that request an interrupt. As the number of devices increases in the system, the daisy chain method will be slower since it requires scanning all the devices starting from the highest priority device. Today we are going to discuss the parallel priority interrupt used to service the higher priority device first and to mask lower priority interrupts. Parallel priority interrupt uses two registers of the same size and each of size equal to the number of I/O devices to be controlled. The first register is called interrupt request register and the second register is called mask register. Bits in the interrupt request register are separately set by the interrupt signal of each device. For example, if the device corresponding to this bit requests a service, then this bit will be set to 1. Priority is established according to the position of the bits in the interrupt request register. For example, this bit is allocated for the highest priority device, the next bit for the next in priority, etc. The mask register is used to control the status of each interrupt request. By means of instructions, it's possible to set or reset any bit in the mask register. So the mask register can be programmed to disable low priority interrupts while a higher priority device is being served. It can also be used to allow a higher priority device to interrupt the CPU while a low priority device is being served. If we have 4 devices, then we should have 4 bits in each register. And if we have 8 devices, then the register size should be 8 bits. According to this parallel priority interrupt hardware, we have 4 interrupt sources: disk with the highest priority, a printer with the next priority, character reader, and the printer has the lowest priority. So the size of the interrupt register is 4 bits. The first bit is allocated for the disk, the second for the printer, the third for the reader, and the last one for the keyboard. If you have 8 devices, for example, then the interrupt register should be of size 8, and the bits in the register should be allocated according to the priorities of the devices. Each interrupt bit, along with its corresponding mask bit, are applied to an AND gate to produce the 4 inputs to a priority encoder. In this way, an interrupt is recognized only if its corresponding mask bit is set to 1 by the program. The priority encoder generates 2 bits, since we have 4 devices, of the vector address, which can be forwarded to the CPU. Another output from the encoder set an interrupt status flip-flop when an interrupt that is not masked occurs. I'll come back to this part after explaining how the priority encoder is designed. The priority encoder has 4 inputs, for example, named I0, I1, I2, I3. 2 outputs for the address and the third output for the status bit. If I0 is 1, this means that we have a request from the device with the highest priority. So in this case, regardless of these bits, the output of the encoder is 00, indicating that device 00 has requested a service. In the case if I1 is 1, regardless of these bits, and provided that I0 is 0, the outputs XY are 0, 1, indicating that the device I1 is requesting a service. And in the same manner, if the devices I0, I1 are not requesting a service and I2 is requesting a service, then regardless of the value, the output is XY, indicating that device 10 is requesting the service. I3 is reached only if all these bits are zeros. In this case, we'll have 1, 1 in the output. If all the inputs are zeros, then the third output is 0. You can note that the third output is 1 if any of the devices has requested a service or is in the one state. If we have any of the inputs in the one state, then this output is 1. Otherwise, it is 0. From the truth table, it's easy to obtain the logical expressions for the outputs X, Y, and IST. Back to our main circuit. The interrupt enable bit and the interrupt status bit are applied to an AND gate, which output is transferred to the interrupt input of the CPU. The acknowledgement signal from the CPU enables the bus buffers, and the vector address is placed into the data bus and transferred to the CPU to start the interrupt cycle. Again, regarding the interrupt status bit, if all the inputs are zeros, here IST is reset to 0 and decoder outputs are not used, since we have here 0. This bit is to 1 when one or more inputs are equal to 1. The output of the priority encoder is used to form part of the vector address for each interrupt source. For example, in our case, for disk, we have 0, 0, 0. So these bits are zeros. For printer, I have 0, 0, 0, 0, 0, 0, 0, 1. For character reader, 0, 0, 0, 0, 0, 0, 1, 0. And for keyboard, we have here 1, 1. The other bits are appended by the CPU to form the complete address of the interrupt service routine. So in the next instruction cycle, the first instruction in the interrupt service routine will be executed. Here we have the interrupt micro operations. After decrementing the stack pointer, the CPU pushes the retain address into the stack. It then enables the INTAC to acknowledge the interrupt. The priority interrupt unit here places the interrupt vector into the CPU bus and from the bus to the program counter. Interrupt enable is cleared to 0 to disable further interrupts. So in the next instruction cycle, the instruction read from memory is the first instruction in the interrupt service routine. For today, that's all. Thank you.